this doesn't need an introduction. You know, we're talking about data, right? Moving away from computation, and this is just one sort of figure explaining that there's a lot of data out there that we're generating, and we really need to find a way to turn that into services and value. Here's a sort of perspective on scaling, right? So this is already an older slide. The data is the same for 2015. This is from James Hamilton, architect of data centers at Amazon. Basically says that the first 5 years of business, Amazon Web Services was about $3 billion annual revenue, and all of that server capacity was added daily in 2012. Okay, so just thinking about how fast this space is growing. And some of these things are sort of reaching their limits, right? So if you think about a big data center, 20 megawatts, 17 times the size of a football field, doesn't matter what kind of football you play. A few $1 billion of investment, and just data, already older data from Energy Star showing that this amount of electricity used is shooting up. So capital investment, huge. Operation, huge. And in the modern world, I think the city of London, for example, financial hub, already 6% of electricity goes into servers and growing at 20%. Now, this wasn't a problem in digital platforms because with Moore's law came also Denard's law, and Robert Denard, Andrew Carnegie Mellon, basically explained that with power equation, C squared F, you have a solid bullet in V, so that you scale voltages down, you get a lot of that power back as you increase density, and that allows you to limit the power per area. Now, if you look at the sort of some of the IHRS projections already for 2014, you see that voltages sort of leveled off. The 2013 already corrects the 2001 curve, and there's a huge difference in the slope right there. So what you end up doing is you go from a modern server CPU, which is a few big cores, sort of your race car, to something like the easy chip, tile-based design, or a cabinet found right, an example of that, sort of specialized core complexity for server workloads. And then that way what you do is you basically get your joule swap back. So that's good. Now the bad news is that what do you do next? The core complexity is going down. Eventually you get to a 5-stage pipeline. So this is sort of extrapolation into the future. This was the last chapter of Nico Sardovel's thesis, saying that even for server workloads, you're not going to be able to power up. If you want to keep the power envelope at 100 watts, you're not going to be able to power up the whole machine. So okay, one good way of dealing with this is accelerators. So here's the panel. On one hand we have data, on the other hand we have efficiency levels that are sort of kind of diminishing in returns. And I'd like to bridge this in data centers, so FPGAs versus GPUs. Okay, one quick slide of FPGAs versus GPUs. FPGAs, reconfigurable blocks, logic, interconnect, block, RAM, I/O. They're enhanced over time in terms of density. There's high-level functionality now available in libraries. Suitable for spatial computation, so that's good. That means arbitrary type of parallelism. And examples have already emerged. Microsoft Catapult is an example. Intel Harp was just announced this year. And GPUs have been around for a long time, right? So we have a dense grid of SIMD ports, multi-threaded, originally developed for graphics, but now sort of with better programmability, you could try to take advantage of data parallelism on workloads. And examples of that is Google announced that they're using in their workloads. Okay, so FPGA's pros, cons, just sort of a summary. Arbitrary logic, arbitrary form parallelism can evolve over time to deal with algorithms. Algorithms are fast changing in this space, right? So even if you think about Catapult with Bing kernels, they keep getting updated, right? You have to deal with that. Now, on the computational density efficiency side, they're not doing so well. FPGAs, you lose in efficiency because it's programmable at a hardware level. And also, just trying to map your algorithms to the fabric is not that easy. The tools are fairly cumbersome. Not a lot of good memory abstractions is another disadvantage. Now on the GPU side, you have really good computational density efficiency, higher level programmability, but it's data parallel only, and it's not really good for sparse computation, and it's also really designed for much denser floating point. So, we have two experts on the topic. We have Desh Singh, who's Director of Virtualization Labs, Altera, and Bill Galley, who's scientist and Senior Vice President of Research at NVIDIA, and they're going to tell us about what they think. Should we go with you, Bill?
Sure, why not?
Yeah, you're closer to me, sorry.
Move the monitor so we can see your slides.
I can sort of tilt this way. So, Dash, I'm going to sit here.
Right thing coming up there. Okay, so FPGAs and GPUs in the data center. This is really a case of using the right tool for the job. If you need to drill round holes, which of these tools would you use? Right? You would use the drill, right? If you want to cut straight lines, you use the saw. So it's a similar thing. If you need lots of arithmetic performance, integer or floating point, you need lots of memory bandwidth, you need tight integration with the CPU, you need to read and write single words into the CPU's memory, or having the CPU read and write single words into your memories, you would use a GPU, because it does all these things better than anything else. So here's an example of how you get all these things. This is a GP100 module that was announced at GTC. The GPU's in the middle here. It has a terabyte per second of memory bandwidth. It has, I'm trying to remember the single precision float of this one. It's on the order of 10 teraflops. And the efficiency fully loaded is on the order of 35 gigaflops per watt. And be careful when you compare numbers like that. Some people will give you a number for just the FPUs. This includes the memory bandwidth, the instruction interpretation, the registers, the power supplies. Everything on this module is in that efficiency number. Now, on the other hand, you need to do something like build something which is going to process gene sequences. You're not operating on numbers. You don't need the arithmetic. Your memory bandwidth needs are modest. You don't need tight integration with the CPU. Use an ASIC, right? That's what people build when they're building things to do encoding and decoding and doing things that don't need the high bandwidth and your arithmetic. Now, if you don't have the volume to justify an ASIC, and turning an ASIC around these days is easily a $50 million proposition, use an FPGA, but realize, and I'm drawing some data here from a paper by Cohen and Rose from the 06 FPGA conference, you're down by something like a factor of 20 to 100x on the non-hardwired logic implementing things on FPGA. So the FPUs on FPGA are great, but you have to feed those FPUs by building multiplexers and sequencers and other structures, and the overhead for that is enormous, which is why you'll never get the efficiency you get out of a GPU on an FPGA. Just to wrap up my summary very succinctly, for arithmetic and memory intensive problems, use the GPU. They're also much more programmable. You can program them in CUDA, in OpenACC, and OpenMP, and very shortly in standard C++. For non-arithmetic logic with modest memory bandwidth demands, use an ASIC, and if you have low volume, use an FPGA, but realize you're going to get this huge overhead and have a really hard time programming. You basically have to write Verilog or the equivalent. If you do use a GPU, you're writing this constant power scaling up. This is a slide from Jensen's talk at GTC. The thing that's circled there is a Pascal module. I just saw you. And you'll have ever-increasing performance going forward. One really telling thing is that there's one company we deal with that started out doing neural network training on FPGAs. And as soon as they tried using cuDNN and doing it with GPUs, they scrapped all their FPGAs and moved over because it was such an overwhelming advantage using GPUs. So for workloads like training neural networks, doing large data analytics, GPUs are really the instrument of choice. So, thank you.
GPUs versus the FPGA in the data center. So the first thing about the FPGA that I'd like to explain to people is that you don't really have software running on hardware. For an FPGA, really it's the software that defines the hardware. And let me explain that a little bit. So say you have a little piece of high-level code, like that single line that I have on the left there, where you take memory location 100, and you can increment it by 42 times whatever is in memory location 101. We all know that compilers can take this stuff, break it down into lower level assembly language type instructions. So you might eventually get to the thing that looks on the right, like the instruction there. It's high level pseudocode for assembly language. So we load the value from memory location 100, load the value from memory location 101, constant 42, do the multiplication, do the addition, and store the result back. Now, if we were to implement this on some kind of processor architecture, this is a very simplified processor, like what you learned about in the first or second year. You know, you might have something that fetches instructions from memory, you got a load unit, store unit. Very, very simple thing that can do some additions and multiplications and things of that nature, and of course a register file. If we were to implement some kind of instruction on this processor, basically you fetch an opcode. The opcode tells the processor how to configure itself, how to configure the data path to do what you want. So here we can load a simple immediate value from memory, put it into a register value. And basically it just tells the data path how to configure itself. Now, if we were to look at that sequence of assembly language-like instructions from a very, very simple program, and were to execute this on a processor, basically what you're doing is multiplexing that same piece of hardware over a sequence of time. So as we go ahead in time, we're loading from the memory locations, we're loading the constant values, all with the same piece of hardware, but we're sequencing through time. We're doing the multiplication, we're doing the addition, we're doing the store back. So this is essentially what a processor is doing. It's taking the same piece of hardware and you're able to multiplex it to implement different kinds of instructions. Now, instead of doing this, let's say we were to have 6 different processors. We unroll this completely in space. So we have 6 processors dedicated each to their own instruction. And if we were able to unroll processors like this, we have something that's fundamentally different. Each processor is now dedicated to a single fixed function. So we can do things like remove the fetch unit because every processor knows what it's going to be able to do, so get rid of that stuff. Now, we have processors that are doing things like ALU operations. Don't need loads and stores, so we can get rid of that stuff. Same things for the things that just do loads and stores. Get rid of the wasted operations. Of course, we have 6 individual processors here. We need them to talk to each other somehow. So we have to wire up the registers and have them communicate with each other in some fashion. So you can imagine just connecting up the register values amongst these processors. And what you're starting to get here is something that looks more and more like a hardware circuit. Of course, there's a lot of waste here. There's some registers that aren't being used and things of that nature. We can just sweep them away. But this hardware circuit is kind of inefficient. We don't really need to match the latency of the original program running on the processors. We just have to match the functionality. So we can essentially retime and reschedule this data path to make something much, much more efficient. And essentially, this is what you do when you try to transform a program to run on an FPGA. You're essentially creating a custom piece of hardware that's going to be dedicated to implementing your algorithm. And on an FPGA, you've got this hardware circuit now, and you can use the FPGA's programmable resources to actually build this stuff for you. You literally have millions and millions of programmable logic elements that you can gang together to form higher level functionality using our configurable routing structure. FPGAs also have the ability to add things like configurable memory blocks, so embedded memory blocks that you can use for scratch pads and caches and things like that. And it's not just these little individual LUTs and flip-flops. You've got things like floating point DSPs that can do floating point multiplications and adds, and these were just introduced in our recent generation of FPGA technology. And when you're done with all of that stuff, you route these blocks together and you actually create a custom circuit to actually go off and implement your particular algorithm. And you can do all of this automatically. You don't have to go off and code this stuff in Verilog or VHDL or some kind of RTL language. We now support software technologies that can be able to take your programs, compile them in parallel language. Here I show an example of doing this in OpenCL, where you're coding something in a heterogeneous environment. And we have tools now that can take the stuff and automatically do exactly what I was showing before in the previous slides. And people are now starting to build up higher level abstractions even with these kinds of tools. So folks have shown that they can take the same kind of technology, build up Java compilation frameworks, and implement things as complex as Spark and Hadoop implementations, that directly map to FPGA hardware. And the thing about when you start using software to define hardware like this, it's not just about defining the accelerator itself. You'll find that there's other fundamental things that you can now do with the FPGA. You can customize how you move data around. So a lot of other kinds of accelerator technologies, you have to move data from the external world, put it into memory, and then process it. That's why you need really, really high memory bandwidth. One of the compelling value propositions of the FPGA is you can just process the data directly inline. And you'll find lots and lots of classes of algorithms where you're processing the data directly from network streams, video streams, external devices of all sorts, and that can go directly into the FPGA, bypassing memory, making for really, really efficient types of computation. And I'll also say that FPGAs are really evolving today to match the needs of today's workloads as well. You'll see that FPGAs are not just the old-fashioned LUTs and flip-flops that everyone pictures now. They have a lot of hardened circuitry. They have a lot of hardened circuitry using things like PCI Express interfaces, external memory interfaces. They have hardened processors on the FPGA. We've introduced the new floating point DSP blocks. You don't have to go off and build floating point operations out of the LUTs and flip-flops anymore. You can build and just implement them directly in our DSP blocks and get tremendous amounts of resource and cost savings by doing so. So I would say the FPGA is really custom acceleration, custom data movement, all using standard software tools. I think that makes it a very, very, very formidable component in the data center. So with that, thank you.
All right. Okay, thanks Dash, thanks Bill. Clearly, a lot of interesting points to debate about between FPGAs and GPUs. I put together a number of questions, and then we're going to also pass to the audience. For those of you who have any questions about this interesting debate between FPGAs and GPUs in data center. So let's talk about programmability, and I want each one of the panelists to sort of comment on this. Clearly, FPGAs are definitely behind in this respect. GPUs already have higher level interfaces than CUDA, although CUDA itself is probably not the best way to express computation, but with respect to FPGAs, obviously they're ahead of the game. There are also rich libraries in the case of GPUs. Is that really a showstopper for FPGAs? Is there nothing that FPGAs can do to sort of bridge the gap? Is there any fundamental advantage between FPGAs and GPUs when it comes to programming interfaces? So I'd like to ask this question from Bill first.
Okay, so in the last panel, somebody made the statement, it's not the ISA, it's the ecosystem, and I think that for programming systems, it's both the programming tools and the ecosystem. So, in a GPU, you have your choice of programming languages. For people who have very parallel programs, they most often get by with OpenMP or OpenACC, where they take their original code, Fortran, often without changes, put in the directives, and they get a very effective GPU program. But for a lot of people, for example, somebody doing neural networks in a data center, they don't even need to go to that level of programming. There are very fast GPU ports of both Caffe and Theanos. So they can basically download some software from the web and be up and running instantly in other vertical areas, oil and gas, financial markets. There's standard libraries that people use and imported to the GPUs. There's very effective standard numerical libraries in the GPUs. So the entire ecosystem is there. It's not so much a matter of it being very easy to write OpenACC code or CUDA code for that matter. It's that there's a huge ecosystem that is built up that makes it extremely easy to take whatever your problem is and get a very large fraction of peak out of a GPU.
Okay, great, Bill. Desh, can you comment on why FPGAs are behind when it comes to programming interfaces? And can they actually catch up? is this a showstopper? Is it, is there something fundamental there?
Well, I would admit the FPGA ecosystem is less mature than the one that's available for the GPUs. I think it really is just a matter of time. I mean, FPGAs have kind of made a strategic shift in the kinds of markets that we're trying to address. The data center becoming something that's very, very large and important for us. And as we saw that market emerge, we had to start to create not only hardware that was suited for this, but software tools as well. And if you look at both big FPGA vendors, Altera and Xilinx, they now support things like OpenCL's first-class citizens, conformant tools. They have C and C++ compilers. You're seeing them announce all kinds of things based on MATLAB and Simulink and other kinds of software environments as well. So this is becoming a very, very large space for the FPGA vendors. And now you're seeing a company like Altera being acquired by Intel. You can only imagine what would happen in the future with a larger software effort focused on enabling these devices. One of the other things that I'll note is that when customers are going off and implementing their own special code, they often can't find exactly what they want in existing libraries. And then when it comes down to just being able to take your algorithm and being able to implement it using some kind of C-like language. And the question then is, what's easier to implement? Can I actually optimize my code for an FPGA or optimize it for a GPU? And I would say that's very, very similar in terms of the difficulty of the types of optimizations you'll encounter when you're going for maximal performance. So I think we're on good footing these days.
Okay, so you agree that eventually they're going to converge. So I'd like to actually try to push this question towards killer apps in the data center world, right? So, and the fact that obviously for programming to happen, we have to push the higher levels of abstraction to higher levels, and DSLs are also emerging as really interesting opportunity to try to map programs, algorithms to FPGAs or GPUs. Do you see a difference there in the use of DSLs and tool chains that will eventually map all the way down to FPGAs?
Well, I think it boils down to the choice. So, take training neural networks. I think is one of the big killer applications in the data center today. You have the choice of a mature set of libraries running on the GPU or sort of an emerging set of libraries for the FPGA. And the only reason you would go for the emerging set of libraries is if there was something else you would gain. But you have better computational density on the GPUs, better flops per watt, better memory bandwidth, better integration with the CPU, and there's actually no motivation to cause yourself a lot of pain in programming because there's nothing to be gained. So I could see if there's something to be gained that they may eventually catch up on the ecosystem front, but unless there's some compelling advantage, it doesn't motivate people to endure pain.
Dash, you want to?
So I would disagree with that. I think a lot of people are looking at FPGAs because they find that they can reach levels of efficiency when you look at both performance and power that they can't achieve with GPU technology today. So we have a lot of customers that have actually moved away from GPUs just because of power reasons and moving to much, much lower cost and very efficient implementations on the FPGA. So that's really what drives people to look at FPGAs and see, can we actually use this technology? And when people have been able to successfully do that, they've been able to show incredible gains from doing so.
What are they doing? Because clearly, if they're doing floating point, they would get better perf per watt on the GPU.
Well, even with floating point, now that we have hardened blocks that are able to do floating point, I think the performance per watt is actually much more favorable to the FPGA than it is for the GPU.
Well, I think the performance per watt of the floating point units themselves is about the same. Right. When we quote our numbers, we're quoting a fully loaded number.
Yeah,
and when you try to do the data supply and the sequencing and all of that with LUTs, you wind up way down.
Right, so I'm also including full system power as well. One of the things about the numbers that you quoted earlier, they were done by academic researchers. And one of the things that you find about FPGA companies is the secret sauce is actually in the software. Right? And I mean, I did my PhD at the University of Toronto where these researchers came from. And the software that we have available in mapping circuits to FPGAs is so much inferior to the things that we have in industry now. And that's part of the reasons that they were not able to really find efficiency and taking circuits and mapping them to the FPGAs and then doing their comparison to ASICs. So I would say internally we have our own numbers where we're able to do these comparisons and find much more favorable.
But if the customers that are trying to put the stuff in the data center can't do that, then it doesn't do them any good.
That's right, but customers using, trying to put the stuff in the data center are not off using academic tools, right? They're using, industry tools, what Altera and Silence and so on provide.
So on that note, I'd like to actually ask Bill. So Bill, GPUs are amazing for data parallel type of computation. What happens if your computation is currently not data parallel? It's still parallel, and you can map it spatially to a fabric, but it's just not data parallel.
Yeah, so it's interesting. So one of our big success stories with GPU programming is actually ray tracing, things that studios like Pixar use to render their feature films. They actually don't use the graphics hardware on the GPUs because that does texture map polygons. They basically run ray tracing as CUDA programs on the GPUs. When we first started looking at ray tracing, it was the poster child for a non-data parallel program. The average warp occupancy, so GPUs SMs are 32 SIMT lanes wide. The average occupancy of that was 1.5 for the ray tracing program. It's now 31. And what we did is we basically took the ray tracing programs. We realized that we were running into trouble. There's lots of rays to operate in parallel, but it wasn't data parallel. Different rays needed to do different things. But you could very easily sort the rays so that at any point in time, an SM would be doing 32 rays that all needed to do the same thing. Most programs that aren't completely data parallel have similar properties, where there's a lot of parallelism and you're simply casing out in a bunch of different cases. And you can actually take these programs in a very mechanical way, transform them, so that they get very good performance on the SIMT.
So if I summarize that, if you have a lot of data, you can map any computation to a data parallel computation.
That's a good way of
Okay,
putting it.
so-
Yeah, you have data parallelism, it's just not regular.
Okay, so
Yeah,
Dash,
and
you
you
want
can
to,
regularize it.
Well,
how do you do on ray tracing?
let me take it to a more practical algorithm. Something like compression, for example, right? Where you're trying to take in a stream in real time and do compression, things like gzip, where it's based on the history of what you've seen before. If you look at how that algorithm is written, it's inherently sequential. It's very, very hard to take it and decompose it into something that's purely data parallel. It is actually much more pipeline parallel. And when you take that algorithm and take its serial implementation and just run it through an OpenCL compiler for an FPGA, you actually get a very, very efficient pipeline parallel implementation that's, just incredible performance when you're
Yeah, but I think you're making my point exactly. So gzip is a case where you're not really doing arithmetic, and you don't really need a lot of memory bandwidth because you're just processing a stream that's coming in. Unlike, for example, ray tracing, where you have a huge scene and a big bounding volume hierarchy you have to traverse. And in those cases, I would say, yeah, if you can afford it, do an ASIC, and if you can't, do an FPGA. But if you've got lots of floating point, you need lots of memory bandwidth. It's also things like a memory system where, because graphics demands high bandwidth memory, we built a memory system in the Pascal generation with stacked memory that's 5 picojoules per bit. If you have an FPGA with an SDDR memory system attached to it, you're off by a factor of 5. You're at 20, 25 picojoules per bit just accessing the memory. You won't get a terabyte per second. I mean, you just don't have enough pins to stack enough SDDR around it to do that. So if you're doing a gzip-like thing, yeah, do an ASIC or do an FPGA. If you're doing a numerical computation like training a neural network, use a GPU. I'm not saying one is better than the other. I'm saying that they're different tools for different jobs.
So on that note, with respect to neural nets, I know that you've been talking about floating point. If you're doing that floating point, things are good. The folks from Chinese Academy, they've been working on doing ASIC for neural nets, and one of the things they show is that it's much better to do fixed point and floating point for neural nets. And there, I think, GPU fabrics are definitely designed for high density floating point. But if you're actually doing high density fixed point, you may lose it.
Well, actually, it's really a question of precision and not float versus fixed. And depending on whether you're doing training or inference, there's lots of papers I can point you at an archive that show that you can get by with 16 and in some cases even 8 bits of precision. And that's one of the reasons why the TX1 that we're shipping right now has support for FP16, because a lot of the neural nets that are part of our Drive PX package for self-driving cars are actually done using 16-bit fixed point. And you can imagine that future GPUs may have very good support for lower precision, both float and fixed as well for the same reason. So I don't think that the type of arithmetic you're doing really matters very much. You can build very dense arithmetic units and make them so you can segment them up for different precision arithmetic. What really matters is that you have a fabric that's optimized for executing arithmetic codes with really high memory bandwidth and close CPU integration.
Desh, do you want to comment on higher level abstractions and FPGAs, DSPs, and how we could bridge that gap with efficiency?
Sure, I just want to get back to the comment about neural nets. So if you look at the way GPUs implement these styles of algorithms, I mean, it comes down to an SGEM essentially, where you're just bottlenecked by external memory bandwidth. And if you were to think about a slightly different way of architecting these algorithms using things like sliding windows and things of that nature, you actually get tremendously efficient implementations on the FPGA without having to go to external memory as much.
Well, I mean, the leading edge neural nets for vision, something like VGGNet, has something on the order of 130 million parameters, right? So that's multiplied by 4, over 500 megabytes of parameter data. You have to fetch that every cycle. That's memory bandwidth. You can't keep that all on your FPGA, even the big ones.
Yeah, so certainly you can't keep that all on a single FPGA, but you can also look at multi-FPGA systems where you string between chips and things of that nature, and then you would also have to compare fairly against a multi-GPU system. But I think in those cases you can actually see really, really good results from doing that sort of thing. So I think it really comes down to thinking about your algorithm, thinking about what is the optimal architecture to implement these sorts of things. And I think all of us are right in the sense that there are trade-offs, right? It really depends on what you're after and how you can actually architect it to take advantage of these things.
Well, I just want to ask a related question because Bill keeps bringing up the advantage that GPUs have with respect to memory bandwidth. I mean, obviously, GPU memory systems are highly specialized for GPU style of data parallel computing, but is that really a showstopper of FPGAs? I mean, can we adopt some of these technologies to FPGAs can certainly benefit from wide I/O, 3D.
Well, I think this is where you get to the the issue of building things out of LUTs. And while he may be sort of refuting the paper from his colleagues at Toronto without giving me another paper that cites better results, which doesn't seem to be kind of that kosher to me, it still boils down to the fact that I can build, say a 6-input AND gate in something like 8 by 10 tracks on an ASIC. And when you look at the amount of area it takes on an FPGA to build the same thing, it's on the order of about 80 times the area. And power tends to go with area, and so you wind up with around 80 times the power. So if you're building your memory controller out of LUTs rather than having it built out of gates the way we build the controllers on the GPU, you're going to wind up burning, and I was taking the 20 to 100 to be sort of nice numbers. I think you can come up with a lot worse numbers. Overhead for the FPGA implementations. And these memory systems are really high bandwidth. If you have a little bit of inefficiency in there, it's going to just destroy your power efficiency. And they wind up needing to be tuned in a way that requires lots of logic to queue up many things. So it's not just a few LUTs. It's going to be a big hunk of logic, and it's going to be quite inefficient to build out of FPGA fabric.
Desh, that's certainly the strong argument for GPUs when it comes to memory bandwidth. Do you want to sure about that?
So first thing, I don't remember the last time a customer came to me and asked to implement an AND gate, right? It's usually a lot more complex things, and you can pack these things together, and you get more efficient results than looking at a little micro benchmark. So that's number one. Number two is that FPGA architectures were evolving, like you said. I mean, recently we announced like 3D integrations with system and package technology. So I think you'll be able to see FPGAs take advantage of the same kind of high memory bandwidth capabilities that the GPUs currently have. And once we're able to do that, you'll be able to see that we can be very, very competitive on these same types of applications that GPUs currently dominate, especially in the world of high-performance compute. I think until that happens, you will see a bifurcation in terms of what an FPGA is good at versus what a GPU is good at. And maybe for a long time you'll be able to see that, right? I mean, an FPGA is not a GPU, and a GPU is not an FPGA. And I think we have to come to a realization, right, we're in a world of heterogeneous compute, and there's probably room for all of these different kinds of devices in the data center. We just have to figure out how do we appropriately create tools that take advantage of them.
Good point. Why don't we open it up to the audience now? We have a number of base questions for the debate. There's clearly, a lot of disagreement as to, which way is a better way to go. All right.
Solar Michigan Tech. In the previous session, it was indicated how important the ecosystem is. My question would be, is it possible that people are developing complexity high algorithms like O(n)² algorithms because it can run on GPU, whereas there could be an O(n) algorithm which would actually efficiently run on FPGA? So the choice of algorithm is driven by the availability of GPUs, right, rather than what is the most efficient algorithm.
I think people tend to
Let
find.
me repeat that,
Okay,
just for the camera, so it was a good question. So in terms of complexity of algorithm, are there algorithms that are more suitable to spatial computing versus algorithms that are more suitable to GPUs in terms of complexity?
Yeah, so I think people find the most efficient algorithm, and then they look at how to map it to the hardware. It's really hard to overcome a weakness in asymptotic complexity with just brute force hardware. I mean, if you've got a lot of data to process, going from end to end squared is a loser no matter what you're doing.
Okay.
So I would agree with that, but I would think that people choose implementations of algorithms ahead of time before targeting technologies. So you'll often find that people will write an algorithm in such a way that it does consume enormous amounts of memory bandwidth, whereas if they could have restructured it even very, very slightly, they could have had a lot more efficient implementation on an architecture that's much more suited for streaming or data flow styles of computation. So I don't think it's essentially the algorithm that people struggle with, but it's more of how do you implement it for maximum efficiency.
Can I sort of push that question again towards data centers? I mean, what do you see as killer applications of algorithms that would be more suitable to FPGAs versus GPUs? Given the complexity of the algorithm, just better suitability in terms of mapping. Maybe Desh can comment on that.
Sure. I mean, one thing that you can immediately come up with for a FPGA is anything that's being processed directly from the network stack and alleviating the operating system from having to do that sort of thing. The FPGA can just take that data in directly from the network, do a lot of network offload, in addition do acceleration on that data before you even have to send it back to the processor. So anything of that style.
So you have examples of prototypes that actually can map the network stack or network-oriented?
People are doing lots of stuff like this today. I mean, if you look in the world of high-frequency trading, for example, you want to offload things like processing of TCP and UDP, put that directly in hardware, get deterministic results from it, without having to make the processor have to handle that kind of stuff.
Yep.
What was the question?
The question was that just in terms of suitability of algorithms, complexity, but more so the algorithms that you would foresee would emerge in a data center or are views of interest in data centers today.
Yeah, well, for GPUs, I mean, it's things that are high arithmetic intensity and high memory bandwidth. The big one today is training neural networks, but also almost any numerical computation falls into that. I mentioned ray tracing, which you actually may not even think of as a high numerical bandwidth, high memory intensity thing, but it is. Let me also comment on the streaming issue that Desh has brought up a couple times. I mean, that's really an issue of reuse, right? I mean, you always try to structure your code, so you need to make the smallest number of main memory bandwidth, main memory accesses, because those are expensive. And so, modern GPUs that have, many megabytes of L2 cache can be structured to stream as well. You simply order your code in such a way that as you produce something, the working set remains in L2 and you fetch it from there and you don't go back out to memory bandwidth. And so maybe apologizing a little bit for having weak memory systems in modern FPGAs, but FPGAs aren't uniquely able to stream. Any machine you can structure the computation so you get reuse out of your storage hierarchy.
All right, Tom.
Tom Money from the University of Michigan. So Bill, in your comments, you pointed several times to the idea that if you have a computation that's not well matched to a GPU, and you can afford to, maybe you should go build an ASIC. But don't you see value in the fundamental advantage that FPGAs have? Whereas an ASIC, it's going to take me 6 months to a year to respin if I discover, oh, I can add a new widget. With the FPGA, I can respin every week, and I can keep incrementally adding to my accelerator or my widget. And that's not possible with the GPU either, right? We can't respin our hardware design every month to add the new thing that we discover only after having multiple nodes. So isn't there value in that advantage?
No,
So let me repeat that question for the camera again. So Tom Wenish from Michigan, a very good question on, there are a lot of algorithms that you like to accelerate in data center space, and these algorithms are evolving. And, would it be practical to go to an ASIC given the turnaround and costs? Whereas with FPGAs, it's much more suitable to be able to, reconfigure that. Go ahead.
Yeah, no, I think it's a huge advantage to be able to, respin your hardware on a regular basis, but you are respinning with this huge disadvantage. I mean, we can argue about whether you're implementing a 6-input AND gate or whether it's a tree of logic with 6 inputs, but you're still off by orders of magnitude, at least 1, and probably more like 1.5 in area and energy for that logic implementation. So if you can be down by a factor of 30, yeah, go do that. But if you need to be at 1x, you really need something which is a little bit more performant.
So Desh, do you want to comment on any of your customers in the data center space that have benefited from being able to reconfigure their algorithms?
So I think that's the fundamental reason that people use FPGAs rather than ASICs in any environment, really. Algorithms are constantly changing. Standards that people are interested in are constantly evolving. You can't just figure out today, this is exactly what I want to implement, and it's going to stay the same until the rest of the time. Especially in the world of the data center, where you don't know the workload ahead of time, and even if people do know what they're trying to implement, it's going to change in a couple of weeks, in a couple of months, and that's where you get a big value proposition from the FPGA. And I think we keep coming back to the question of the efficiency of implementation on the FPGA. I would point out that anything that's programmable has inherent inefficiency. I mean, people can now measure how inefficient an FPGA is because it's programmable hardware. But something that's software programmable, in the conventional sense, has inefficiency. It has circuitry that goes off and fetches instructions. It doesn't just have the pure functional units that are off doing the actual compute. It has all the stuff around it that's routing data to the compute. So everything has an efficiency. It's a question of quantifying that.
Right. We can quantify that. If you look at the S sum of a Maxwell, the X1, the Tegra part, in the SM, half of the energy goes into the floating point unit. So our inefficiency compared to if you just wire the floating point units to one another is 2. I think that an FPGA would be very hard pressed to come anywhere close to that number.
So again, but you're doing this for one specific type of algorithm. Right? I mean, let's say you can't just measure the hardware itself, right? It's sequencing the instructions and how much efficiency you get over the lifetime of the algorithm itself.
Right, that is running a particular actual application, the next one.
Let me go to the other side. Go ahead, James.
All right, so the question about both trail and cache. So, well, your respective platforms, they stand to that FPGA and GPU. Do you feel they are, in fact, a good fit for data center applications? And if it's not, if they're not, then what are some of the things you want to do differently if this, if data center were to killer app to drive future GPU and future FPGA?
Well, let me repeat that question. So maybe that question is actually related to one of my supplementary questions, which is there's a lot of stuff that's going on in the data center world. And this question was James from Carnegie Mellon, which may not be a good fit for either acceleration by GPUs. Okay, and actually, I'm the right person to be asking this question because we've been working on this for the past 15 years. A lot of the services that are really spending most of the resources in a server are actually just pointer chasing. And in modern world, there are a number of services: data serving, caching, web serving, web search. This is just basically unstructured, data structure traversals, and it's not data parallel, right? So are we even going after, is there a good fit for data centers, these kinds of accelerations? GPUs versus FPGAs, we can go with Dash first.
Sure. So I think in the world where you have to do things like pointer chasing, like traversing some kind of graph, and you just have huge data structures that are off-stored in some kind of memory system, let's presume it's on the processor's memory system, the FPGA is hanging off like an accelerator. You do need to go to technologies like shared virtual memory. So that's something that we've just introduced with our OpenCL compilation framework. And we can do this over various kinds of transport mechanisms like QPI. So as you start to see FPGAs become more tightly integrated with processors, and especially having interconnect technologies where you can start to share some of the same memory space, I think it makes it a lot more attractive to do these sorts of algorithms. Because before that, all of the stuff that you would be able to do in an FPGA was essentially offloading memory to some kind of accelerator, having some processing, and then coming back, or having that kind of disaggregated model where the FPGA is off just doing its own thing, processing from the stream, and then sending results back. So this opens up a whole new world of algorithms that we can now implement with a much tighter integration. But I think it is really too early to say how that stuff's going to all pan out.
Bill?
Yeah, so I think GPUs are already, I think, pretty well suited for the data centers. Many very successful deployments suggest, and they're actually very good at pointer chasing. And a lot of people will do graph algorithms. I think the current Graph 500 winners for the small size graphs, the things that will fit into the sort of 32 gigabyte memory of a big GPU, are fastest on GPUs because they have the fastest memory bandwidth. That if you have enough parallelism in the graph, you can be doing all those pointer chases in parallel. They're also very good at chasing pointers in the CPU's memory. The upcoming Pascal generation of GPUs has NVLink, which makes that a sort of 150 gigabyte per second path to CPU memory. So you can basically use all the bandwidth of the CPU memory from the GPU just as if it were the GPU memory. The place I think that GPUs could do better at integrating into the data center, I think, really has to do with networking and access to the network. Right now you tend to chop your problem up and have little pieces of the problem on GPUs. If people thought of data centers more as if they were big HPC machines with a PGAS global address space, you can do some really interesting things doing puts and gets over the network from GPUs and be able to run very large problems, very large graphs at whatever the bandwidth that your network would be going to.
Go ahead.
Jason Kang from UCLA. First I want to make a comment and I have a question. The comment is that I think FPGA is not only a field of customization for computation. In fact, I think in our experience, a significant advantage is the customization for the memory access. We have a DAC paper last year, for example, for tensor computation. You can prove that you can achieve architecture maximum reuse at the minimum kind of on-chip, off-chip, on-chip traffic, right? So that I just want to make that comment. The question I have is that is the form factor ever a consideration? Because from my conversation with some of the folks, they're saying it's hard to put in a GPU in a 1U server or 2U server. That seems to be where FPGA has a natural advantage. I just want to hear whether whether you have a roadmap coming forward to overcome that.
Yeah, well,
let me jump in because there was a comment and a question there. I think each one of those deserve having a bit of a debate about. Jason Kang from UCLA. The comment was that, in fact, FPGAs are not just a good fabric for accelerating your computation, but also very good at customizing your memory accesses. Would you like to comment on that, Desh, maybe? And then Bill?
Certainly. So I think one of the interesting things that you see with being able to customize an accelerator for your application is to be able to create a memory system that's ideally suited to feeding those functional units as well. So applications in the data center where you do things like ranking documents and scoring them, you often find that the things that you're trying to do are very, very irregular lookups into large tables in off-chip memory. And one of the ways that you can get around that is to build a very efficient hash table so that you don't have to go off to off-chip memory if you don't have to. When you look at implementing that stuff on an FPGA, you can make a gigantic multi-ported hash table incredibly trivial in software. So being able to customize that stuff for the application gives you incredible efficiency in applications like that.
Bill, you want to rebut that, or?
Yeah, no, I actually tend to agree with that. I mean, since you have a bunch of block grams and you've got to structure them as you want, you can sort of build your storage hierarchy however you want. I mean, we have lots of L1 caches, scratch pads, and L2 cache. So we can, for the same size of working set, we can sort of build data structures that emulate that, but we don't have the ability to change the replacement algorithms and the mapping. I think that actually is an advantage of FPGAs, but again, it's something where you're down to writing the Verilog level, you're not going to get that out of OpenCL.
Okay.
So I wanted to comment on this form factor.
Yeah, so
Yeah.
the second question, the question actually was about form factors and advantage when it comes to form factors. So, go ahead.
Yeah, so I mean, if you saw the photo I had in my slide deck, that's what's called an SXM module, and that was a Pascal one, which we're not shipping yet. But we are shipping SXM modules with Kepler now, and so you don't need to have a PCI card form factor to put a GPU in your server. In fact, many people ship 1U servers with GPUs in them using our SXM modules, which are small daughter cards. I mean, they're smaller than the size of an index card, with the GPU, all of its memory, and its power supply on one module. So the small form factor exists.
Josh?
So I would just echo what Jason said. I mean, you'll find that a lot of customers are choosing FPGA just because of the amount of density in terms of ports that they can get into these server systems.
Go ahead.
Shadi Ajib, University of Lille. Just wondering about the role of dynamic reconfiguration in this context for the FPGAs.
So I didn't get your affiliation, but
University of Lille in France.
okay. And the question was, I apologize. I was thinking about your affiliation. I forgot. Yeah. It was a very brief question. I remember.
I'm wondering about the role of dynamic reconfiguration, FPGAs, dynamic reconfiguration in this context, in the context of accelerating.
Okay, so let me see if I
Can I
heard that
comment
correctly.
on the last question before you repeat his?
Okay.
Yeah, so the thing about form factor really came down to density. And what I've observed dealing with a bunch of different data center customers is density ultimately becomes a question of energy efficiency. Most data centers are limited to so many kilowatts per rack, somewhere between 20 kilowatts and 50 kilowatts, depending on which customer you're dealing with. So it really depends on who is able to deliver the best performance per watt on the algorithm. And right now, GPUs are very good at doing that on things that involve stuff that looks like dense or sparse linear algebra.
Okay, so now going back to the question from the gentleman from France. The question, if I interpret it correctly, has to do with FPGAs in the past have had an advantage that you could dynamically reconfigure, and a lot of effort was spent in reconfiguring fast enough so you can deploy whatever new algorithm you have. What role does that play in a data center setting, and is that something that's actually of great value?
Yeah, I think it's incredibly valuable actually, because in certain aspects of data center compute, workloads are just completely elastic. You can't predict ahead of time exactly what a customer is going to be running, especially when you have things like multi-tenant systems. And then you want to be able to allocate acceleration resources off to these people where you don't know exactly what's going to be on the FPGA. So you want to be able to dynamically swap things in and out depending on the current needs of what the system is actually doing. So things like dynamic or partial reconfiguration, as we call it, are big technologies that enable that sort of thing.
Okay. If I understand in the current setting, for example, accelerating search, neural nets, or whatever machine learning kernels you have, they're mostly accelerating the training, and then that's sort of offloaded onto the sort of reconfigurable fabric, and it's highly time-consuming. So in fact, the configuration time, if you're doing it once every 24 hours, it's not as big of a so do you see that reconfiguration speed playing a great role in the future?
I think in the future it will be. I mean, currently the way that FPGAs are deployed, the configuration doesn't change all that often. But I think there was an earlier question about what kinds of things would you change in the FPGA or GPU architectures to really enable even more
penetration into the data center. That would be my answer. If we could have much faster reconfiguration speeds on a much finer grain as well, I think that would allow us to swap things in and out much more quickly and enable us to do very, very fine grain offloading to FPGA.
I just have to point out that in a GPU, this is called jump, and it happens in a couple cycles.
Well, actually, I'd like to go back to that. In the context of GPUs, that basically means that you have to reprogram your kernels and whatever new algorithms you come up with. And in a programming interface, whatever that may be, if it's CUDA today, tomorrow.
When you were talking to him about writing the code, you're talking about just loading it,
Just
right?
loading it, yeah. But let's sort of reformulate that question. You know, would GPUs actually have an advantage over, you know, if you have a new algorithm and you want to just deploy?
Well, I think, you know, with the question of the original one, which is dynamic reconfiguration, I mean, people basically have GPUs deployed to run multiple algorithms today, and it literally is jump. I mean, the code is actually all there, and they simply say, okay, you're going to run this code now and jump to that, you know, thing. So yeah, the kernels are all coded. Now, you know, the length of time writing the original kernels is another issue, and that's where if you're writing in, you know, OpenMP, you know, a directives language is clearly the most productive mode of operation, and moving down to a language like CUDA or OpenCL would be next, and then if you have to write Verilog, like you would for a highly tuned FPGA algorithm, that would take the longest.
All right. Let's go to the other side.
John Demi, Columbia University. It seems like today's discussion thus far has been centered primarily on GPUs and FPGAs in the current configuration. If we look out further, 5, 10 years in the future, how are they going to compare? And more fundamentally, I think you'd agree that it's largely about spatial versus temporal compute models. Fundamentally, what is going to work out better in the data center? Which compute model, and how are these things going to work?
Okay, so let me you know, sort of interpret that question and then for the camera as well. John Denny from Columbia. It's a very good question. So, you know, we've talked about convolutional neural nets as an application today. I guess other machine learning kernels. Let's sort of extrapolate 10 years from now, if we can. What would be the advantage and disadvantage? How would they fare? So let's go to Bill.
Yeah, so you know, I think GPUs are going to continue evolving the way they have. By the way, I don't think it's a question of spatial versus temporal. I mean, GPUs get their performance from parallelism. That's spatial, and you know, it's not a spatial versus temporal thing at all. It's two different types of spatial architectures. The GPUs are going to evolve where they're basically going to, you're going to have more streaming multiprocessors. They're going to be faster. You're going to have a memory system that's deeper with more on-chip storage and higher bandwidth off-chip. So I don't see any radical changes coming. I think it's going to be more and better of the same things. It works very well.
Okay, Dash, FPGAs on steroids 10 years from now?
I mean, I can't speak for exactly what we'll be creating, but the way I see the world is that we're moving to more and more heterogeneous systems on chip. I mean, FPGA technology has really evolved to now incorporate things like hard processors, and you can imagine that trend even going further and further. And we might find that 10 years down the line, we have, you know, an architecture that looks like hybrid GPU FPGA coming from many different companies. We have multiple processors as well as some of the advantages that you get from hardware reconfiguration as well. So we'll see what evolves.
So I just want to bring up one last question and then maybe an opening, sort of closing statement from you. Can you comment on integration, right? So you know, we've seen GPUs in the discrete form and these integrating them on chip. Now, you know, with FPGAs, Catapult is a discrete form of FPGAs. Now we're seeing FPGAs integrated in CPU. Does integration between GPUs and FPGAs, is there advantage to either one? You know, how would you foresee that coming? Bill?
Yeah, so we see an advantage with integrating with CPUs. In fact, an approach we've taken is what I call logical integration, where, you know, through the development of NVLink and ultimately coherence technologies, you have very tight coupling between the CPU and the GPU memory, both very high bandwidth, very low latency, and transparent sharing of memory. We think it's much less important whether things be physically integrated, where they're on the same die. So we do that in our low-end processors, things like the TK1 and TX1 for mobile things, because economically it makes the right sensor. It's much more economical to deliver one monolithic die with 4 or 8 ARM cores and a GPU than it is to make that 2 separate die on package or on a circuit board. At our high end, we actually see the economics pushing the other way to motivate the logical integration, but keep it physically separate chips, which allows you to make both the CPU and the GPU chips much more powerful and to rev them independently of one another. As to an FPGA, it's interesting to think about. I haven't seen any applications that would really demand that.
Yes?
So, I mean, I really can't comment on what's going to happen with Intel and Altera as their relationship gets closer and closer, and processors and FPGAs maybe more. But today, what you see with FPGAs is that we're incorporating things like ARM processors and having very, very tight integration on the same die between the processor and the FPGA. And that enables all new kinds of classes of algorithms because you have a very low latency communication link. That allows us to do very, very fast offload on these kinds of devices. We're also looking at the same kinds of technologies for logical integration, where we're doing over things like QPI to allow us to have shared virtual memory between the FPGA device and the processor. So I think in the future you'll probably see closer physical integration as well.
Okay, so let's have a closing statement since Bill went first. We asked Dish about a
Sure.
quick closing statement.
So I think this has been a really good debate, and there's been lots of points of contention, but I think just as a scientist, I think you'll find that there are applications for both GPUs and FPGAs, and it comes to picking the right balance for your particular data center or your application. And I think it's a big opportunity for all the researchers out there to go off and build tools and figure out exactly how we enable this.
Bill?
Yeah, so I'll go back to my opening statement, which is choose the right tool for the job. GPUs have the best performance per watt for things involving arithmetic, the highest memory bandwidth, and most efficient in terms of picojoule per bit memory bandwidth of anything out there, the tightest integration with the host CPU. And so if that problem you're doing involves those, use a GPU. If you're doing something like zip, I guess was the example given, where none of those things fall into the category, use an FPGA. I think it's not a question of one is better than the other. They're good at different things.
All right, thanks a lot. That's
What's that?
We have a break?
We have 10 minutes.
Speaking of 4 o'clock, 10 o'clock.
All right. Well, we were